Now I'm pleased to introduce our presenter for today's training, William Conlon. As Senior Project Manager with RPS Klotz Associates, Mr. Conlon is responsible for managing the studies and modeling of stormwater projects that meet the needs of our client. Mr. Conlon has been a hydraulics and hydrology design engineer for 15 plus years. During this time, he has been responsible for handling many hydrology and hydraulic related studies and designs. He has been involved with the evaluation, design, and construction for multiple master plan residential communities, site-specific drainage facilities, and governmental infrastructure projects for several cities, counties, and state agencies around Texas. Mr. Conlon is experienced in detailed hydraulic delineation and evaluation of watershed drainage areas, closed conduit and riverine hydraulic analysis, and floodplain mapping and modeling. Prior to RPS Klotz Associates, he was a senior project engineer with Jones & Carter and was an integral part of the TSARP remapping of Harris County flood control insurance rates maps, including HECRAS analysis, GIS, floodplain map generation. Mr. Conlon has also managed several mud projects while working in the H&H department. William, take it away.
Thank you very much, Brett. Good afternoon, everyone. Just want to get started and I guess jump right in. We'll start off with a quick introduction history of the suite toolbar and the drainage infrastructure analytics program that the City of Houston is currently using and how it got started. Next, we'll get into how the actual toolbar works, and get in. The third topic will be an update to what we call the design event adequacy. We'll get into some of the details on that when we get to it. And then the fourth and final topic will be how the toolbar has been expanded from more than just a stormwater tool to actually help with the roadway evaluations as well for the City of Houston. So with that, the SWEET toolbar, and I guess to start, SWEET stands for the Stormwater Enhanced Evaluation Tool. And it started with a quick analysis that we had performed for the City of Sugar Land to help them kind of prioritize and identify some problem areas, more on some data-driven results more than subjective political pressures. We made a presentation of that work at the Texas Floodplain Managers Association conference several years ago. This was probably back in 2008, 2009. There was some City of Houston reps in the audience, and they talked to us after the fact and wanted to see what it could do to help the city. And so we started working with the city on this project about 2009, and it has grown significantly since then. It actually started before the Rebuild Houston concept, but it has become an integral part of that project and helping the city staff identify the problem areas and where some of those money should be spent. A little history of the City of Houston for those that aren't from the City of Houston. It's about 600 plus square miles, about 2.3 million people. Typical storm sewer designs are for a 2-year event. Back several years ago, the storm sewers were sized for the 3-year, but that rainfall was actually more like a 1-year to today's standards. So our current standards are about a 2-year storm sewer with a 100-year analysis for the sheet flow level of service. We get about 55 inches of rain a year, and it's pretty flat. And on top of that, everybody knows how bad the traffic is around town, not only with the volume, but also the pavement condition. And so having this tool be able to help the city prioritize their traffic and pavement improvements was a big step for them. For the drainage side, again, the city is relatively flat. We do get some significant rainfall. I think a couple years ago we had over 100 inches of rain. So there is a significant amount of floodplains in the city. Anybody that's seen the floodplain map know it's as much floodplain as there is non-floodplain. And so with the growing population, the city has taken it upon themselves with the Rebuild Houston initiative to start to develop a fund to fix the pavement and drainage aspects within the city. So how does the toolbar give some kind of innovative, some interesting ways to do it? The Sugar Land stuff we did, again, was a data-based system based on true data sets We looked at how to weight each of the categories and started running that through some simple spreadsheet type analysis. It allowed us to use objective inputs as well as taking some of the subjectiveness out of it, and it really started to alleviate some of the push from loud voices and make it more data driven. The way the city expanded on that was we took it to the next level with integrating it into GIS and working through setting it up so it's more of a tool and repeatable and defensible. And just to kind of brag a little bit, we did win the CEC award, I think, for the gold medal for the projects under $2 million. I believe it was last year. Just a little bit of self-promotion. So some of the challenges the city faces, again, it's so flat, it floods often, but it floods all over the place, and some of it is based on the floodplains, but there's also just as much flooding that occurs outside the floodplains in areas where the storm sewers are either insufficient or the inlets are insufficient or too much sheet flow comes to an area that wasn't accounted for, and this was 50, 60 years ago in some of the older areas. So being able to identify those need-based areas and work with the city to prioritize and rank those projects on a worst first concept really was the key. It allowed to be, again, more reactive, not reactive, more objective, and take a lot of the subjective inputs. In effect, it takes the politics out of the decision-making process. And so having the pressure honestly off the councilmen and councilwomen to say that there's a reason why their area is not getting a project, or there's a reason why their area is getting a project, it allows that to be a little more defensible with the public realm. And the use of the technology, I mean, having LiDAR, having the GIS capability to be able to process citywide data really helped the city take it to the next level, as well as let it be that non-political aspect. And that was one of the big pushes, the big forces behind the toolbar. So how does the actual toolbar work? I guess the long answer is it is a geospatial analysis tool to rank and prioritize overlapping data sets with a prioritization matrix. And then that's a pretty big, long sentence, so we'll get into a little bit how it works. Again, with the objective methodology, each of the data sets, each of the pieces of information is given a weight and given a priority. And so once that is set and agreed upon, and there was a significant amount of back and forth, once all that is set, it pretty much is standalone and it's agreed upon. The updatable and easily updatable and dynamic nature of it is along the lines of that if one data set changes, you don't have to rerun the entire process. You can just update that one data set, incorporate it into your results, and get some new outputs, some new prioritization areas. It helps with the planning. Once you know your worst first areas, some of the output that comes out of this tool really helps the city start to put together their 5-year CIP and their 10-year CIP. It goes from this tool to the first step is, okay, let's do a pre-engineering report on the top 10 areas, and that's kind of a high-level review of why is this a bad area. And from there, once you identify, is it drainage, is it streets, is it historical flooding from the rivers, then you start getting into a preliminary engineering report, a true PER, and so that's the next step. And once the PER kind of identifies the problems in a little more detail and gets into some of the cost around it, the city then can reorganize, re-rank their CIP and start identifying budget constraints. And from there, the next step is to actually identify the projects for design, kick it out for design, have it come back, go to construction, and actually improve an area. So it's about a 3 to 4 year window with about 1 year per step. And anybody that's familiar with the city of Houston, their project SOQ and RFQ process is significantly driven by the output from this tool. So it's kind of a fun way to help the city. with it being consistent and replicable, the fact that the data sets are inputted, the percent and the weight scores are all fixed, then it allows you to really identify the areas that come back. And so the next person 2 years later should still get the same results, and we've shown that they do get the same results. So the fact that it is repeatable really adds some validity to the tool. Transparency kind of goes back to the politics side. The results come out, the data set can be processed because it is a GIS attribute that comes out at the end. Can be manipulated and presented in any fashion, so it really helps the public see why their area is the priority, or why their areas is not as high ranking as some of the others, because they may be more of a green than a red, and we'll get into some of that. And that data-driven kind of goes back to the objective methodology, that it's defensible. It is, once you've identified it and explained it, it's very hard for the public to argue and for the politics to get in the way. So we talked a little bit about weighting and what does all that mean. So we need to identify the needs first, and once you identify, actually need to identify the categories. And that was one of the hardest parts, is the city had about 10 or 12 categories that they thought would be important in identifying drainage or street problem areas. And we'll get into some of that in a little bit down the road. But once you identify the categories, then you need to identify the needs. And the needs are where it doesn't meet the current level of service, or the current need. And for storm sewer, that may be the 2-year event. It may be the 10-year event. For flooded structures, anything that floods is unacceptable. For street ponding, it may be 18 inches over the curb is excessive, and that becomes a non-acceptable level of service. And so those areas get flagged. And so once you have your data sets and once you have your categories, you then start to try to figure out the weights. And this is where we get into the political side, where they have their input. And there was a pretty good back and forth. I think there was the stakeholders, shareholders meeting, shareholders group, and they went back and forth on, flooded structure versus a street with 2 feet of ponding in it, or a repetitive loss versus a significant amount of 311 complaints for ponding in the street, and which one gets a higher priority. And so we'll get into some of that. So with the categories the city currently uses, and kind of talk about this in terms of data sets and buckets. So the buckets are the 4 bullet points off to the left, and we have a bucket of drainage conditions, we have a bucket that deals with flooding, we have a bucket that deals with mobility, and the mobility is storm sewer impacts to mobility. And then a 4th bucket, and actually, honestly, it's a second full run we do with the street and the pavement conditions independently of the storm sewer analysis. The city has potential to overlap these two and let both data sets help rank the projects. But because they're separate funds for each of these, at least up to this point, they have them as separate runs within the toolbar and separate data sets and separate outputs. So within the drainage side, we have the DEA, and that is the Design Event Adequacy. That is the level of service of the storm sewer system. It is a 2-year level of service, and does either a pipe or a roadside ditch conveyance system for a certain section meet or exceed the 2-year level of service. And so we'll get into how that's created. That's kind of the cool part about this tool, and the most recent efforts we've been expending have been to update that DEA coverage. And so we'll get into detail on that one. Another data set that goes into the drainage bucket is the 311 complaints. And these are phone calls that come in from the City of Houston 311 line, or updates to the website when somebody is driving down and they notice there's significant ponding. They'll hit it on their phone on the app and upload it to the city, and so the city will run with it and keep that data set. So it's a pretty cool concept of incorporating that. Flooding condition comes back to structural flooding complaints. We get some data with Harris County Flood Control. FEMA also has repetitive losses, as well as just normal flood insurance claims. So there's a lot of information that comes out of this that is in effect proprietary, that the city has, that's really not public information, for lack of a better term. So we work with them to update the toolbar and how it works, and then the city has their data sets that they run. And so the city of Houston does a pretty good job of running the toolbar and identifying their problem areas. And then the mobility aspect is impassable streets or streets with over 2 feet of ponding. And that's one of the data sets that we help them create through some GIS LiDAR evaluations. We looked at bowls within the city in areas that don't have a defined sheet flow corridor, to where if the storm sewer were surcharged or overloaded, where are some areas that would have over 2 feet of ponding before it could cascade to the next low point. And again, this is based on LiDAR, so it's the 2008 LiDAR. Everybody's still waiting patiently for HGAC to get their updated version, but that's where we sit right now. And the other tool that they run, the other physical run that they make is with regards to the street and the pavement, and that goes into the level of service, but for the street conditions. So we have the A grade and the level of service B and C, as well as pavement condition, and that we'll get into some of that detail a little bit, but that's the rutting and the potholes and the pavement cracking and whatnot. Again, we talked a little bit ago about how the city originally had 10, 12 data sets, and maybe even more than that, that they wanted to consider using. But as they found a lot of these data sets, for water for wastewater example, we've been talking to them about trying to incorporate that in, but because the water wastewater comes out of a separate fund, the city has a different ranking and prioritization tool for those improvement projects, and it works for them pretty well. So it's not a need right now. Talk about health and safety, for example. A lot of these data sets, they weren't full citywide coverage, so it left some voids. So if an area had a health and safety issue or an environmental historical issue, then others that didn't have it, it would kind of be excessively weighted towards those areas, and it really wasn't the breaking point or the decision-making need for a true storm improvement project. But the health and safety, one of the cool considerations with that is if you're looking at a street that is right next to a hospital and everybody needs to get on that street to get to the hospital, then that street, if it is flooding, just like a street maybe 10 miles from a hospital, the one near the hospital may have a higher priority because it's more traveled or more needed for these emergency situations than a street that is kind of out in BFE and far away. It just helps with that priority. But because that wasn't one of the tools they've been using, it is something that's considered for a potential data set in the future. So these are the systems that the city is currently using. Again, the DEA adequacy, the level of service, we'll get into that a little bit. That's why it turned red. We'll get into more details on that. But it is a polygon, and it's dealt with the drainage areas and how that drainage area for that system has a level of service, either under a 2 to 5, a 5 to 10, up to 100-year level of service or greater. Other data sets that go into the drainage bucket are flood complaints or areas that pond over 2 feet. And again, the flooding complaints are point data sets, and that's like 311 flooding complaints. And so this data set image is the overlapping of all the 311 point files that the city has. This is from back in 2013-ish. So once you have a point file, or once you have a raster file or a polygon file, you need to start finding ways to overlap them and get them in a similar data set that is citywide coverage. And that's the ultimate concern, is to try to get all this information to a citywide coverage. The data sets that go into the flooding bucket, again, it's structural flooding, FEMA repetitive loss, and the NFIP losses. Structural flooding comes from flood control or more local data sets and information. FEMA repetitive losses are structures that have always flooded or historically flooded. And the NFIP losses is a similar data set, but it's for individual claims. And again, some of this information the city kind of keeps under wraps, and for good reason. But they've got it to run in their tools, their runs with the toolbar whenever they need it. And then regulatory, that bucket deals with the impassable streets, and these are underpasses or streets you just can't get across. So we've talked about the data sets themselves, and we've talked about the buckets. And so this is kind of that agreed upon ranking and weighting of each of the data sets and how each bucket overlaps with the overall score. So the DEA adequacy, the level of service coverage, is 40% of the drainage bucket. And if you look at the blue, the drainage bucket is about 38% of the overall score citywide. And so you can kind of do the math and figure out which ones are more important and which ones are the key topics. And the flooding conditions, repetitive losses, is a pretty high rank out of that 38%. And so these are how the ranking and the tool gets set up. And these are all on a sliding scale. So once the city determines the rank, they set the scale. But in terms of the toolbar itself, the toolbar has the ability to readjust those rankings as needed. We talked a little bit how the point values and the point data sets come in as raw data. And so being able to take that and rasterize it in a citywide coverage with an intensity map, this is simply one of the processes the tool does to turn it into a citywide raster. And they do the same thing with the DEA coverage. The polygons get converted into a raster to where there's individual cells that have a score. And so once each data set gets rasterized, we go through and we set up the ranking of each of the buckets. And so this is kind of how the tool works. You see it's running in the background. We've got some of the different rasters set up. But again, each of the data sets has their ranking. You can slide the sliders. You can manually type it in. But as long as it's less than 1, you've got a correct ranking set. And it shows us how we can overlap our buckets and our data sets. So this is the rasterization of just one data set. So FEMA losses, again, 55% of that one data set. And you see some hot spots up in here. Within that bucket, kind of go back to here, FEMA repetitive losses is 55%, but also in that bucket you have structural flooding and NFIP losses. So when you add all 3 of those data sets, you start to amplify some areas or you start to soften other areas. This dark red now is not as high priority because there's other areas that have all 3 data sets overlapping, and so this area becomes more priority. And then again, once you have the one bucket set, you can overlay that bucket against all 3 buckets, and you end up with a citywide overall score, and you get some hot spots down in here, some hot spots up near Kingwood. And then the final output is an aggregation layer, and the aggregation layer that the city currently uses is the Lambert grids. And the Lambert grids take the city and split it into about 6,000 grids, give or take, and they were set up through the CenterPoint Energy and the power company set up their Lambert grid system. And so it works pretty well to give us just a good, simple grid system across the city. And so you'll see that throughout the whole city, based on all 3 buckets and all 7 data sets, we get some hot spots kind of in the Brays Bayou area, down near Clear Creek, and up in the Kingwood area, or Spring Creek area, excuse me. And so these are areas that get ranked as worst first based on the data sets that are incorporated and based on the ranking of those data sets. Again, the data sets can be manipulated however is needed. You can apply a higher ranking to others. You can take certain data sets out if you're only looking at structure flooding. If you want to look at just the storm sewer, you can run the tool with independent data sets, independent buckets, or all together. So the output that comes out, again, we've got some of the range of 6,000 plus Lambert grids. Each one has their own feature ID. It gets ranked 1 to 6,000, and you'll see within each bucket, each Lambert grid gets a ranking. And so this bucket appears to have some really bad flooding, but the drainage system's not that bad. But when you combine them all together, it gets the highest score. And so this helps the pre-engineering report identify why there's a problem. Anything with a high flood score that has a low drainage score is probably a problem because of riverine flooding, especially with mobility and passable streets. You've probably got something that is more riverine, and honestly, it may not be a City of Houston problem. It may be a flood control problem, and I say flood control problem, may be caused by a river more than something the city has control over. And so looking at that, they may help them prioritize. This may be right on the bank of Spring Creek at Cypress Creek, and that may be why it's a confluence, and it may just be a bad area. And so those flooding issues may not be something the city can solve. And so setting that up and understanding why and how really helps the city focus their funds and focus their priorities in trying to solve their problems and fix their issues. So now we're going to delve into now this is kind of the nerdy part. This is the H&H geek coming out. How does the design of inadequacy come in? And what this is the city had back in the late 90s, early 2000s, their CDP coverage. And the CDP is the Comprehensive Drainage Plan. And it tried to identify the level of service of the majority of the drainage storm sewer system citywide. LIDAR wasn't really available a whole lot at that point, so drainage areas were relatively large. They were relatively driven by development and parcels more than terrain. So it had a good system and it worked pretty well, but there was no roadside ditch coverage. And within the city of Houston, the roadside ditch is about 30% of the city's drainage infrastructure. So to update the CDP with what we're calling the DEA coverage, we had to update the closed conduit system, and we have a lot of technology that helped us refine that process, as well as determine the level of service for the first time for the roadside ditch coverage. And how that was taken was kind of interesting. The operation and maintenance group within the city of Houston was getting a grant to go survey the roadside ditch to help them prioritize maintenance projects. And lo and behold, unknown or unheard of in government work, two departments internal to the city of Houston actually talked and actually realized they could do something together. And so with a little bit of assistance from the planning department with the O&M, the operation and maintenance group, they were able to pick up just a few more data sets whenever they went out and surveyed it, and we were able to try to incorporate that roadside ditch information into a drainage area delineation as well as a capacity calculation. So again, we look at the areas in the city that are served by roadside ditch. It's about 30% of the network, give or take about 10 to 12 million linear feet of roadside ditch in the city of Houston, which means there's about 20 million linear feet of closed conduit serving all the areas in the city of Houston. And so with that 30+ million linear feet of storm sewer system, the city of Houston now has, through our update to the DEA, a network model built in GIS, as well as drainage areas delineated for every single manhole and every single, we call it point 3 and point 9 on the roadside ditch survey. And there is now full coverage and full drainage area delineation, albeit on a relatively high level for the whole city. And that's 33 million linear feet of system that was analyzed. So being able to use technology really helped us cut that process time. It took about 4 to 6 months, but could have taken a couple of years. So this is the typical cross-section that was surveyed. It was an 11-point cross-section, picked up everything from the right-of-way to right-of-way, relatively high level. Again, weren't too concerned with some of the grade breaks or some crazy weird areas. Tried to pick up top of bank, flow line, edge of pavement, street center line. And so what this, I kind of talked about points 3 and points 9. Those are the flow line points at every cross-section. And with the 11 million linear feet of roadside ditch that was surveyed, they took survey at every kind of upstream and downstream of every culvert, as well as a couple spots here and there in the middle of some long roadside ditches. So we were able to extract out the points 3 and points 9 and try to analyze the drainage area that got to that point, as well as the amount of flow that got to that point, and the capacity of that system. So the rational method was used for both the roadside ditch and the storm sewer. The drainage areas were cut at each point 3 and point 9, and we had 40 to 50,000 drainage areas just on roadside ditch, and 100 to 110,000 drainage areas served by storm sewer that were determined at the manhole locations. So key manholes that had the pipes on them. We took the impervious raster the city has as part of the Rebuild Houston program, and we're able to overlap that with our drainage areas to determine the percent impervious of each drainage area. And with the rational method, once you know your drainage area and your percent impervious, for any given storm event, the I could be calculated, and that gives you the flow at that point. Then to determine the capacity, for the roadside ditch, we were able to kind of go back to this. You were able to identify the cross-sectional area of each ditch. We can get into that in a little bit, as well as pipe diameter taken from the gems. Now, everybody knows the city of Houston knows gems, knows that that's only as good as the paper it's written on. Gems is as best information we had to try to analyze 20 million linear feet. We do have some survey data and some as-built we looked at to try to get comfortable on some of the bigger systems, but for the most part, it works pretty good, and it gave us a starting point. So with a that mine? Sorry about that. When you have your cross-section, you got your points 3 and points 9, as well as using the LiDAR data. One of the reasons we did in the LiDAR was at each of those points 3 and points 9, we took the flow line, the point 3 and point 9, and we exaggerated it. We burned it into the stream. We dug it about 1,000 feet down. And what that did was just to help us provide a low point for the storm water or the sheet flow calc to collect the water into the ditch at each point. We also took the road center line and we built up a wall. We raised it up about 1,000 feet to help just identify the left and right side of a street so that we had a drainage area on either side. And then we also performed this fill sinks routine to help provide a natural sheet flow path that gets there. This isn't meant to be technically correct. It was simply a hydrologically correct cross-section that we did to help us focus the flows at each of those key points. And with all that, a lot of the process was done with automation and scripting we did within Python. Python was chosen because it's a pretty strong program. It's pretty easy to use. It was free, and it works well with ArcGIS and ArcMap. The city, we took the DEMs, and there's about 67 DEMs within the city. Each one of those was extremely large to process, so we had to cut them into 16 grids. Allowed us to really simplify the process and speed up some of our processing. And then we ran our drainage areas, and we delineated everything to try to get it processed. Each DEM provided about 1.5 gigs of data, and a significant amount of that data was just all the little routines and tools we had to set up and create to process all the data. So once the DEM was run, actually take that back. Before the DEM was run, we realized through some of the analysis that we had overlapping potential of drainage areas that may come to a point that's right on the edge of the DEM. So we went ahead and buffered every DEM about a mile out, and that allowed us to pick up these drainage areas or a storm line that might fall just on the edge, and we could really get everything processed. So we took the 60-something DEMs across the city, cut them into their 16 grids. The buffer was performed, and we have both the roadside ditch and the storm sewer pipes burned in and allowed everything to try to hydraulically create the drainage areas based on the manholes or the center flow lines. But one of the problems we ran into was with the direction of the ditches and the pipes. Some of these areas were simply clicked when it was drawn in space in GIS. They started at the top and clicked down to here, and it just happened to put the direction of that flow this direction. Well, we had to go in and fix those, because if you were to delineate a drainage area right here, or I'm sorry, at this point, it would only pick up this part and this part, because this is shown to be draining back. So this would not add to this drainage area. You wouldn't get that overlapping additional flow coming to it. So we set up a process where we started flipping our culverts. And we did this around Christmas time, which is why we picked red and green. But if the start was a green and the end was a red, we made sure that every green had its own red, and we weren't having all greens or all reds. And so this process allowed us to start flipping lines and flipping the culverts and flipping the direction, simply because somebody might have clicked left to right instead of right to left. And so once we had our network set up, we started delineating the drainage areas. It was all about just the collection of flow and how everything got to a certain point, and we could build up our drainage areas as they get to the channels. But one of the issues we ran into was we had the grids, and if the cell fell in a grid, but there was a process of cells to just circumvent it, just skirt by real faintly, we would have a false drainage area, and this area should be coming to this point. Just because it was just outside the grid, it wouldn't get picked up. So we added a series of mini lakes routines, and it just provided a buffer on that point to pick up all the cells that touch it, and it really allowed us to pick up the true drainage areas that would get there. And in similar fashion to the network connectivity, we would have the areas that were drawn the wrong direction or just didn't snap. They didn't clip right up to the collection point. So we had to go in and we had to extend the lines or snap the lines and really get a drainage area put together. So once we have the network, we were able to start cutting our drainage areas. Again, this is where that 1 mile buffer comes into play. You have some drainage areas that fall outside that still drain back, so we want to make sure we had all that in there. But just on one DEM, we were getting 4,000 to 5,000 drainage areas, and again, we had 67 DEMs, so we're looking in the range of 150,000 to 160,000 drainage areas within the whole city of Houston. But these are just the drainage areas at each point, and this doesn't help me if I've got a system that's cascading down 24-inch, 36-inch, 48-inch pipe. I want to know what the overall drainage area is at that downstream manhole. So we had to find a way to start merging the drainage areas and overlap them as they get down. So you'll see this one, drainage area G, starts as, I'm assuming, a 0.9 at Roadside Ditch, and it picks up its area, and then it cascades down, and it plus the new stuff in F comes to F, and it crosses over and goes to a 0.3 in the Roadside Ditch, and then it goes into a pipe at D, and it continually cascades down. So we get the full drainage area that gets to this manhole, and that goes into the A as part of our drainage area. So once we know the A, we extract out the percent impervious from the city's infrastructure plan. And for each storm event, we calculate the I based on atomic concentration for each drainage area. We use the city's equation for the rational method, and we're able to determine a peak flow for the 2, 5, 10, 15, 25, up to the 100-year event at every manhole and every 0.3 and 0.9 of the Roadside Ditch. So with the pipes, it's relatively easy to identify the capacity of that pipe. We simply took the pipe diameter and we made some assumptions on the velocities. For 24 and 30-inch pipe, they flow about 3 feet per second in big events. As you start getting into bigger pipes, you have bigger drainage areas, and you usually have higher velocities. So we started taking the area, the cross-sectional area, and we're getting the continuity equation with Q equals VA. So the area times the drainage cross-section, the cross-sectional area times the velocity gave us a capacity. Now for the Roadside Ditch, we needed to know what was the max water surface, what was the control point, what was the highest the water could be in each ditch. And we wanted to make sure that it didn't exceed the right-of-way, and we also want to make sure that we didn't allow it to exceed the pavement. So we have an edge of pavement, top of bank, flow line, top of bank, and right-of-way on both sides. And so if the pavement was higher than the right-of-way, then the right-of-way controlled. If the right-of-way was higher than the pavement controlled, and vice versa. But that only gave us the control elevation. From that elevation, we needed to determine the cross-sectional area within the ditch. So we took the area between the cross-section line and our known control surface, control elevation. But if it was an area that was outside of the ditch, then we had to exclude it. But if it was an area inside, we did a series of equations, and we have this polygon and this polygon plus this polygon gives us a summation of the cross-sectional area, all done through spreadsheet and Microsoft Access. And again, once you had your area, you could determine your velocity. We used the slope of the LiDAR. We used the slope of some of the survey data and determined our velocities from the slopes. So once you know the cross-sectional area and the capacity, and you compared it back to the drainage area delineation and the flow that actually gets to each point, you were able to determine which was greater? Was the capacity greater than the 2-year flow? Was the capacity greater than the 5-year flow on down to the 100-year? And we had about 10,000 areas in the roadside ditch alone that were inadequate of the 57,000 points that we looked at, 57,000 drainage areas. So this was for the drainage system for the roadside ditch. We have a similar table for the storm sewer, but in general, this was the amount of stuff that we analyzed. And to correlate it, this is one of the outputs that comes out. Again, the darker the shade, the lower the level of service. All the red is for roadside ditch. All the blue is for the storm sewer. And to correlate, we took some of our roadside ditch problem areas, and we overlapped them with 311 complaints, repetitive losses, structural flooding complaints, and areas that had a low level of service were the areas that we had complaints in. And so it really correlated pretty well and gave us comfort in our calculations. And our final topic is, how can this toolbar be used as well for the street analysis? The City of Houston used to have their own street assessment vehicle, but recently they've gone away from that and subbed it out. But they drive the whole City of Houston in a 2-year cycle and pick up pavement condition, potholes, roughness, rutting types, and all this is measured while the van drives the streets. And so they have all of the pavement picked up, as well as the traffic volume. They have counts, and they've got a historical set of data for that. So they run that every 2 years, and it goes into the tool, and we get these kind of prioritization and ranking output. So the one on the left is the pavement condition ranking. This doesn't include the traffic volumes, but that's pavement ranking. And when you overlap that with the traffic volumes, you start to get this similar aggregation layer, similar hotspot of street and stuff, street and road problems. So this is kind of the summary that comes out of it. About 33% is inadequate, and that deals with both pavement condition and traffic capacity. So this helps them identify their problems. And this is one of the outputs that comes out. So this is a 50-50 split between pavement and vehicle capacity ratings. And this was years ago. This is a hypothetical storm. This is a hypothetical run, just to give a sense of what it looks like. So East Lake Houston between 1960 and Cordon is the worst street in the city based on these parameters. And again, this is a hypothetical run. This isn't the data the city uses. This isn't information that they're using to set it up, but this is kind of what it looks like when it comes out. And so to kind of conclude, I mean, one of the potential uses, the cool things the toolbar does is you can output the data in several formats. You've seen a graphical representation. You've seen a table set. Because it's GIS, it has attributes. It can be manipulated color-wise. It can be manipulated region-wise. It can be, the tables can be ranked by different categories and whatnot. So once it's run, you can re-rank and reprioritize however you need. You can rank it based on each council district seat. If you want to identify the worst ones in council district B, you can get a 1 to 5 of district B. And so it allows you to really manipulate data once it comes out because it is GIS driven. And so some of the, kind of to wrap it up, I mean, it does provide that transparent and defensible process. It takes a lot of the politics out of it. It helps to identify that worst first, and the city can really take it and run with it. There's data sets already out there. There's not a whole lot of reinventing every year. City gets with FEMA and gets new data sets and just plugs them in and reruns it. Because it's dynamic and updatable, it's simply because a new data set comes in, they can rerun that new one. And as you saw, we were able to process the entire City of Houston to provide a level of service of every pipe and roadside ditch cross-section for the entire city in a matter of months. And it correlates really well with the output. So with that, I'd like to thank everybody for allowing me to present it and talk about the tool, and turn it back over to Brett to try to close it up.
Thanks, William. Great presentation. How difficult would it be for other cities to utilize this tool y'all have?
It's actually pretty easy to use. The only hurdle is the data sets themselves. The tool was set up simply because it's sliding scale on each of the ranks and each of the weights. There's 4 buckets, as many data sets as you want can be put in each bucket, but it requires the data sets. And so, you know, we've had discussions with other cities around the state, and it all kind of comes back to, if they have a really substantial GIS system and pipe network or 301 complaints or repetitive losses, then it can help pretty easily.
Okay, great. Another one, did you use pre-existing drainage areas, or did you have to make area polygons for this?
That was one of the things. We actually calculated these drainage areas based on the 2008 LIDAR, and the points where each drainage area was determined was the manhole or a point 3 and point 9. So we have 150,000 drainage areas that we delineated ourselves on behalf of the city from scratch.
Okay. Are the output data sets available on GEMS online database? You may explain what GEMS is for people outside of...
Yeah, GEMS is the Geographic Information Management System the city uses. It's they have it online. It's the GIMS. And there are some data sets on GEMS that are used, but I don't believe the output from Suite is ever put on GEMS. Again, that's kind of the internal to the cities. Their function, their use is a little more proprietary in their decision making. The city project manager is the one that may be able to answer that question, and I can help anybody who wants to talk to him as well. But the data sets that go into it, some of them are from the system that's on GEMS. Some of it is proprietary from FEMA, but the output I don't believe has ever been posted.
Okay.
And to clarify, I think the reason for that is because they change it every year. They usually run the toolbar in October. So they run a citywide data set in October and process the data through November, start to identify their needs, and that's effectively where a lot of the RFQ stuff comes out in the springtime, is a lot of that process gets done around those times. So they'll update the data sets if there's a project that was recently completed, but it wasn't able to be incorporated in the data set. They may manually weed out that finding because they know they've already fixed it. It may be a number 3 ranking project, but they've already fixed it last year, so they may just take it out. So that's why it's kind of a work in progress every year, and I don't think it's necessarily, for lack of a term, public consumption.
Okay. Can this be used, say, like on a yearly basis in order to kind of track progress on funding to help with voter decisions for future bond elections and whatnot?
Yes and no. There is the ability to use it to show how an area 3 years ago is now better. There really isn't at this point a funding aspect to the toolbar runs in terms of knowing what the improvement projects are going to be. But it does help. It does help the city identify where the problems are. It does help the city identify why the problems are there, because you look back at the table, if it's flooding driven or is it drainage infrastructure driven, which one has a higher score. But for each of these hotspots, for each of these, you kind of go back to, it's back to aggregation layer image right there. You know, this one has 4 or 5 cells that are red and dark orange. But they may be flood-based because of flood control channels, or it may be an area that already got fixed. And so if the same area keeps popping up 3 or 4 years, then you know you've got something to go work on. But this is really a high-level just identification tool. The pre-engineering reports and the preliminary engineering reports that come out of the next 2 phases really identify the projects and the cost associated with each one to help them identify their true CIP.
Okay. I think that's about all the questions. Really appreciate it. go ahead and wrap it up here. Thank you again for participating in today's ASC Texas Session webinar. As mentioned before, individual registrants should receive an attendance acknowledgement without further action. For those attending with a group, the site coordinator will receive the PDH certificate for distribution. June's webinar is going to be on fiber reinforced polymers by Larry Goldberg with Nuvacus Corporation. I invite you to visit the Texas Section website, texasasce.org, to register for the webinars, to learn more about the association, and to take advantage of the benefits of membership. You can also watch 2016's recorded webinars on demand and earn PDHs. I'm always available for your questions and hope to hear from you soon. Thanks for your attendance. Have a great day.
This concludes today's webinar. Thank you for joining us. The session will now close.